Aloha. This presentation is about the Comprehensive Nuclear Test Ban Treaties Infrasound Technology Roadmap. It was delivered by Patrick Renard in Working Group B40 and by Georgios Haralabous at the European Geophysical Union. They are the leaders for this project, and please contact them for further information. I'm presenting this material on their behalf. Let's talk about the future. No, it's not really, more precisely, various futures, multiple futures. They're intersecting, overlapping, and interconnected futures. And their timelines extend to a horizon of 7 years, where in principle, they should reconverge. At the desirable feature of all these futures is sustainability. The rationale for the Infrasound Technology Roadmap itself is essentially maintaining relevance. And relevance is a very delicate balance. If you go too far, you're perceived as being irrelevant, and if you lag too far behind, you become obsolete. So it's part of it is finding that balance. And overall, it's a call, it's a desire, it's a need for adaptation, cooperation, and also resource stewardship. So it's hard to argue against cost efficiency, protecting investments. Ultimately, we have to prioritize all these lofty goals. And ultimately, this roadmap is trying to synthesize that. What are the priorities of this project? And we have to enhance the operational efficiency and effectiveness at the International Data Center and the IMS divisions. In particular, improve the readiness for on-site inspections, as well as other emerging challenges. And by emerging challenges, there was a mention yesterday of technological steps. That's an emerging challenge. There's also, of course, geopolitical challenges and geophysical challenges. And ultimately, we have to promote the transparency and neutrality in data services. So these last two slides are fairly transportable. They're really hard to oppose. They're lofty, high goals. But how do we go about turning these goals into our reality? Well, we build a framework. Within that framework, we have a set of roadmaps with sub-frameworks. The Infrasound Technology Roadmap is the first of what will probably be a variety of these technology roadmaps that are embedded within the Foresight framework. The Foresight study has a 20-year timeline, far more than I can envision presently. But the CTBTO has put this together, and there are two posters on this presentation, and these are the poster numbers. And also, I'll refer you to Amit, who's sitting right on that gate there, and he will guide you to the Foresight project. And if you, for some reason, miss him, you can go to the website that is posted there. All right. The roadmap is intended to be a catalyst for action. Now, we have to agree on a set of needs, build a consensus of some kind that can provide a framework to coordinate technology development within 7 years. I actually work with catalysts quite a bit. I have to fix all the surfboards in my family, and there's always something broken somewhere. And the trick with catalyst is, most resins, be they fiberglass or epoxy, they will take forever to cure. They will take days, weeks, months. And so you need to expedite that by adding just the right amount of catalyst and harden them. And the balance is if you add too little, it will take days to weeks. You might as well just wipe it off and start again. If you add too much, it hardens too quickly, and then you don't have time to finish your work, and the material becomes brittle. So before you begin to do this kind of work, you have to assess what is your work statement, and then tailor your mixture to that particular application. So our aim was to define the work at hand, and to do so, we decided on a participatory, inclusive, and iterative approach. We grabbed up a whole list of topics and focus areas that came for the foresight study. It was very comprehensive. We trimmed those down and sent those out to 62 members of the Infrasound community, incorporating academia, government, industry. And then we asked them, could you please help us? Give us a measure of impact and feasibility for all these topics. So we got back a measure of this. You know, how feasible is this topic? How important is it? How is it going to impact the operations? And so in terms of numbers, we got a 90% response rate on 119 topics. That's a lot of technical topics and a lot of patience of many of the members of this community. And the next phase of this is to actually start looking at the validating this and inviting contributions from partners. The next step to that was assigning a measure of relevance. And only the CTBTO can do that, really. So the distillation of this response from the community, they were kind enough to give us impact and feasibility, and then CTBTO assigns the relevance to it. And it boiled down to 4 main operational capabilities. So this became a capability-driven ITR, where the capabilities are congruent with the operational mission. And so this is an important slide because it provides the foundation of the roadmap framework that's embedded within the foresight framework. So on the first level is at the station level. It's at the IMS station performance, sustaining and optimizing that level. And the next level, it has a bit of synergy, which improves the IDC station processing. So both of these occur at the station levels. What is this station? How can you optimize? Where is it at? How can you tailor the response of this station to its environment? The next level is a little bit more meta. It starts going down to the network processing and improve the IDC processing at the network level. And finally, we go to performance monitoring and testing. And that's a fairly large scope of work. That's a very broad way, broad task in which a lot of these previous capabilities fit into. On the capabilities, let's go one by one. Would you select subtopics? All these 4 are at the station level, and they all have one thing in common. They all begin with a set of definitions and standards, a common language, so I can tell you, oh, this is what this metric means, this is what this measurement means, this is what the time window is, and then progress to the point where you actually can roll it out throughout the IMS network within a 7-year timeline. The first 2 items involve the capture process, the sensing systems, and they're in many ways engineering problems. These are okay. How do we make sure that we can end up at the end of 7 years with full frequency calibrations once every year for 80% of the network? Now, the sensors is the transduction. The wind noise reducing system is fairly unique to infrasound. This is WNRS. It's those systems attached to the sensor to keep the noise level down, because at every step of the way, the wind is our nemesis when it comes to detection. The next 2, the optimized station design and station quality control, is more of a synergy between engineering and geophysics. You're doing station tuning at this level. You're saying, okay, this station is in the tropics, it only has a few degrees of variability per year. This is in the Arctic, it's got 80 degrees of variability in the year. And you defined a set of systems that are optimized to the environment and the conditions there. And also for quality control. Tropical stations, Arctic stations, different seasons. Some stations get wind in the middle of the day. You build that into response. Which brings us, of course, into our detection capabilities, signal detection. Every station is different. It's a little bit like like misery. Each one's different in different ways. So they all have their own environments. And they begin with, again, defining a set of standards that we all agree with. And this slide is a real good example of Asynchronous intersection timelines and symbiotic futures. The signal classification is inherently intertwined with the signal detection. You first of all have to define what is a signal. Then you go one step of the way, and then you can classify it. So you can see that this particular capability is going to have this intertwining motion, where you actually have a back and forth between the two. And not only that, there might be a little time offset where your signal classification will go a little bit further than the signal detection, a bit of a lag, because you're fitting into each other. On the topic of signal detection, going back to the subject of these catalysts, last week we had a technical meeting for quantifying the seismic, acoustic, signal detection, and events definition algorithms. This was a CTBTO sponsored project, and Pierrick Miel and David Brown will be good points of contact if you want to follow up on this. And its objectives are to define the framework for the detector evaluation and establish a protocol, a sequence of events where we start with methodology and common metrics, and of course, identify contributing partners. So this is an example of a capability that, I mean, he made it to a roadmap because it was important, and now is feeding it back to the community with a clear procedure where to start. So we're still at the standardized data quality metrics, and then starting to define the procedures. The third capability is to improve the IDC network processing. And this is, again, a very large problem that relies very strongly on detection. And the aim, of course, is to reduce the analyst workload by 50%. That is, again, a kind of target that's reminiscent of Reykjavik. If you can do 50% now, and you do it again, and you do it again, you have this exponential convergence down. So it's a nice way to start. There's a logarithmically based convergence. And so this is our aim for global association. We need to get the detection down, and then go in there. So the sequence is there. And this is the next topic, refinement for climatology. It's rather unique to Infrasound. You see, all these capabilities, every single one of them, noise, propagation, detection, associations, all of them are vulnerable to the atmospheric variability at all time and spatial scales. Our sound is a measure of variability, for better or for worse. So we have to account for that, how to build that variability into our detection capabilities, global associations, et cetera, And that is a fairly brave problem to tackle. Yes, oh, sorry. All right, finally, the fourth capability is one where many of our capabilities, maybe of a previous timeline, should reconverge again. It's an all-encompassing timeline in a way. It's kind of like a sound check. You know, you go into a room, bang, 1, 2, 3, testing, right? Well, we can use volcanoes, we can use meteors for this. It's a way of checking whether the system is working. And for example, you could use microbarons because they're there all the time. They're right in the bandpass of interest of the 1 kiloton test, and they're continuous. If a station is not picking up microbarons, it's probably worth looking at it to find out what's amiss. It could be just windy, and that in itself is interesting. It's valuable information. It is important to build a certain level of porosity into each capability. It's nice to see linear trends that are decoupled, but that's just not reality. We want to have, to allow interrelations between topics and innovation to be allowed to percolate into the roadmap. And again, there's 119 topics, and we pick a small subset of them. These are scientific topics that have technical merits. There are books and numerous papers written on them, and they have strong potential crossover into the roadmap. However, they exceeded the IMS and IDC requirements at the time of their evaluation. Their time to impact was deemed to be beyond the 7-year horizon, but there's always that possibility of unexpected discoveries and breakthroughs to be able to contribute to the roadmap, and we have to build that porosity in there, otherwise we lose on that. Of course, there's also disruptive approaches. Things happen quickly this day and age. So, in closing, The Comprehensive Nuclear Test Ban Treaty Infrasound Technology Roadmap is driven by operational capabilities that are congruent with its mission. And it does permit the potential of knowledge transfer from unexpected breakthroughs in research and technology. And it invites feedback from the community and contributing partners. There's one more item that was brought up by Florian in his talk yesterday. He came up with the ARIS Grand Challenges. It's a really good thought. There's a few things we like more than a good, worthy, noble challenge. And the ARIS poses a number of challenges: environmental monitoring and natural hazards, and how to build a workforce and advanced technology. Not only that, but get a deeper understanding, not just of our Earth, but also other planets. And this is something that is fertile, it's pluripotent, and we have a few opportunities this year to revisit this. We have the Infrasound Technology Workshop, we have an Acoustical Society of America meeting in December, and American Geophysical Union meeting in December with infrasound sessions. So I will invite the community and interested parties to participate in these. Thank you.
Thank you very much, Milton. We have time for a couple of questions. Is there any questions? Okay, I don't see any.
I have a question if there's no other questions. In your association algorithm, I can't hear too well, so
Sure.
bear with me. I think we're using Global Association, GA now. Is there any direction for NetVisa as far as association in the future?
I would like to refer, maybe we can talk about that. That's a very lengthy question, but if you don't mind talking that afterwards, I can direct you to all the right people doing this. Okay, thank you.